So we've designed, manufactured, tuned and tested our cavity, and the important next step is to actually measure the thrust that we're going to get from this thruster. But before we do that, we clearly need to understand how much thrust we're going to get out of it so that we know how to design the thrust measurement apparatus. Basically, what sensitivity is needed, what the level of errors are likely to be. So to actually predict the thrust that we're going to get from this cavity, we need to solve the thrust equation, which we've come across before, which is T equals 2p QU dF divided by C. So that's 2 times the power times the unloaded Q times the design factor divided by C. We've said that the design factor is equal to Vg1 minus Vg2 over C. This is the difference of the guide velocities at each end of the cavity divided by C. And you must note that this requires the subtraction of two relativistic velocities. Vg1 is of the order of, it's close to the speed of light. Vg2 probably a tenth of the speed of light. So these are two very fast velocities. And so we need to turn to Einstein to get the true value when we add or subtract these relativistic velocities. And it's actually given by his equation, V equals V1 plus V2 divided by 1 plus V1 V2 divided by C squared. So we can take this correction factor and apply it to the thrust equation, and we get the thrust equation you can see there. And then we need to turn the equation into guide wavelength terms rather than velocity terms, because these are the terms that we're going to get out of the actual design of the thruster itself. So we have the equation now that T equals 2p QU over C squared times lambda naught over lambda G1 minus lambda naught over lambda G2 divided by 1 minus lambda naught squared over lambda G1 times lambda G2. To finally turn this equation into something more useful, we need it in terms of the diameters of the cavity itself. And we've already seen that to do that we need to take into account the cutoff wavelength. So what we have is lambda G1 equals lambda naught divided by the square root of 1 minus lambda G divided by a lambda C1 all squared, where lambda C1, this is the cutoff diameter, the cutoff wavelength at the diameter D1, the large end, is KNM times D1. And similarly, we can calculate lambda G2, where lambda C2 is the cutoff wavelength at the small end, D2. We'll now look at the value of DF, the design factor, in detail for the SPR flight thruster. We've said we have an equation for the design factor, which in this case includes the relativistic correction factor. And we've seen that for the flight thruster with D2, the small end diameter at 97 millimeters, D1 the large end diameter at 200 millimeters, we get guide wavelengths lambda naught, which is actually the free space wavelength of 77.37 millimeters, lambda G1, the guide wavelength at the large end at 87.75 millimeters, and you can see how it increases to lambda G2 as the diameter comes down, so that lambda G2 is 331.61 millimeters. Now, from the equation, we get the design factor of 0.8168. So let's have a look at how this varies, and this is shown in the the plot to the right of the slide, where basically the red line shows the value of the design factor for a fixed D1 equal to 200 millimeters, and the blue line shows what happens if we increase D1 to 300 millimeters. If we look at the plot, you can see that as D2 approaches the cutoff diameter of lambda, cutoff diameter of 94.36 millimeters, the design factor DF approaches a maximum of lambda naught over lambda G1. And this maximum actually increases as D1 increases. For a D1 of 200 millimeters, which is the design of the flight thruster, we get a maximum design factor of 0.882. Now this, remember, is when D2 is approaching cutoff diameter. So the absolute maximum DF you're going to get for a D1 of 200 millimeters is 0.882. If we increase D1 to 300 millimeters, we can increase the design factor, and in fact it goes up to 0.949. Clearly, you can't carry on increasing D2 because you have the dimensional restrictions on the design of the thruster itself. If it's too big, it won't fit on the payload. But nevertheless, you get a significant increase if you increase the large diameter. If we look at basically the other end and watch as D2 approaches D1 at 200 millimeters, the design factor actually approaches 0. This is not surprising because what we're actually doing is increasing the small end diameter until it's as large as the large end diameter. So we end up with effectively a cylindrical cavity rather than a tapered cavity, and you'll get no thrust out of it. The design factor is 0. Indeed, if you increase D2 to be greater than D1, so in other words, we're reversing the taper, the design factor will actually go negative. You can see that as D2 approaches D1 at 300 millimeters, the design factor also approaches 0. Now, one of the interesting design exercises you can do is to calculate the ratio of the temperatures of the two end plates. And if you calculate the ratio of these, you need to obviously calculate the dissipation at each end, which effectively you can get from the design factor. Then you take into account the area of the plates themselves. You can see the thermal effect on variation of the end plate diameters. And we've already said that this is actually particularly valuable to validate the whole theory of EmDrive. And for the flight thruster itself, we got, as we've said before, a calculated ratio of 0.66 against a measured ratio of 0.69. And this actually was a clear validation from an independent view of the thruster operation, in other words, from a purely thermal view of the thruster operation. As well as the design factor DF, the other important term we need to look at for calculating the thrust from our thruster is the value of the unloaded QU. Now, to calculate QU, you need to know the two diameters, D1 and D2. You need to know the axial length L0 between the two end plates. And you need to know the surface resistivity, RS, of the material on the internal wall of the cavity. You calculate RS from the value of the conductivity for silver at 20 degrees C, which is 6.29 times 10 to the 7th moles per meter. You can calculate the surface resistivity, RS, from the equation given, where F0 is in megahertz and lambda is 6.29. And for 3,873.6 megahertz, the surface resistivity comes out as 0.0156 ohms per square. The other term you need in the equation for QU is a value for the mean diameter. We simply take the average diameter, DM, as 148.5 millimeters. So if you put these factors into the equation you see below, a somewhat complicated empirical formula, then you calculate a theoretical QU of 73,249. However, we've said that there is a problem in approaching this theoretical QU, mainly due to the tolerances of the cavity itself, giving rise to different path lengths between the two end plates, which gives rise to a phase error across the wavefront and decreases the value of QU. For the actual flight thruster itself, we measured a loaded Q of 27,586, which at first sight seems very low, but you must realize that the thrust depends on the unloaded Q, not the measured loaded Q. And if we've got the input matched correctly, we've already seen that the loaded Q, what we're actually measuring at the input of the cavity itself, is half the unloaded Q. Therefore, the actual unloaded Q of the cavity is 55,172. If we put this into the thrust equation for a power input of 1000 watts, we get a thrust of 301 millinewtons. So we've calculated a specific thrust of 301 millinewtons per kilowatt. If we compare this with the measured results of, rather the mean of the measured specific thrusts over a large number of test runs, then that mean value comes out as 326 millinewtons per kilowatt, which is pretty close to the theoretical. Close enough for us anyway. So how do we measure thrust? Well, clearly the first thing we need is a sensitive balance that measures the force that's being applied to it. And we've got a flight thruster which weighs 3.2 kilograms. We've got a test set that will produce 500 watts at the input to the thruster. And this is going to result in a typical output thrust of 163 millinewtons or 16.6 grams. So what sort of balance would we use? Well, we actually used an Avery Burkle FC161. It's a good quality electronic balance. We'll measure up to 16 kilograms and we'll give you a resolution of plus or minus 0.1 grams. Now, the important specification of any balance is what's called the spring constant. And for this balance, the spring constant is 13.9 kilograms per millimeter. So this is the amount of movement that the balance pan will make for a given load on it, 13.9 kilograms per millimeter. And we'll see the importance of this in a minute, because obviously the first thing that you think about doing, and everybody thinks about doing this, is simply to place the thruster on a balance, switch it on, and expect to see a change in the weight that you're measuring on the balance. Now, this doesn't happen. Physics doesn't allow it to happen. Basically, conservation of momentum and Newton's laws says it will not work. Why? Well, if we look at the little diagram I've given on the slide, you can see that the reaction force R is opposite and equal to the thrust T. There must be a reaction force. Newton's law says there must be. So that if you assume that the mass m is greater than the thrust that you're going to get out of this beast, then clearly you will get no change in the balance reading B. When the thruster is loaded with a mass greater than the thrust, then no thrust will be measured on a simple balance. You clearly need to have a more complex balance mechanism, and it must be a balance which can move. Therefore, the spring constant that we've already mentioned is an important factor. We saw in the previous lecture a general view of the test equipment for the flight thruster, and now we'll look in detail at the balance which is used to actually measure the thrust. Now, this is what I call a composite balance because it actually contains two spring elements. One is a simple suspension spring from which the majority of the weight of the thruster is suspended, and the second spring is effectively the spring in the electronic balance, the spring constant that we've already mentioned. So we will look at a mathematical model of this later, but you can see obviously there are two spring constants involved in this particular thrust measurement apparatus. An important consideration is the change in distance between the two suspension points. That is the point at which the top plate meets the spring, the suspension spring, and the point at which the whole weight of the thruster is transferred through to the balance pan, if you like, on the electronic balance. The problem here is that when you turn the power on to this thruster, you immediately start getting a temperature change, and we need to minimize the effect of this temperature change on the balance reading. So one of the first things we did was to make sure that the top fixing point of the suspension spring and the bottom base of the measurement apparatus itself was kept constant by using invar rods to separate these 2 points. Now, the other point that you must bear in mind is that as soon as you put power into the cavity, it's going to start to expand. Therefore, the length between the two suspension points, if you like, the spring and the electronic balance, will actually start to increase. And we'll see how this is used in the mathematical model that we'll look at in a minute. We've said that there's a need for a preload on the thruster if we're actually going to comply with the conservation of energy, and we can adjust that preload by the top adjuster on the rod, the suspension rod from which the spring itself hangs. The other important point, of course, is that the thruster itself must be effectively free to move, therefore it mustn't be constrained by the input circuit supplying the power. And we've already mentioned that we use something which I've termed as a free waveguide coupling. The tweeter itself, we've said, produces vibration, therefore it's mounted on a separate table, and the free waveguide coupling actually bridges between the two points, between the fixed point, which is the output of the circulator, and the moving point, which is the input of the thruster itself. Now, between the floating side of the waveguide coupling, there is the input cable, and this is a fixed coaxial cable, and indeed provides one of the main thermal elements of the whole setup. That cable can get quite hot under full power operation. Here we see a drawing of the free waveguide coupling, and you can see that it is in fact a custom-built device comprising a fixed waveguide section which is mounted on a brass base plate, and the fixed waveguide section is inserted into a floating waveguide section, which is then fixed to a waveguide to coax transition. So the two sections of waveguide, both floating and fixed, are made from copper sheet, and around the whole assembly there is a third section which is the EMC shield, which basically is an attempt to minimize the leakage out of this particular device. The idea is to keep the gap between the fixed waveguide and a floating waveguide as small as possible. I mean, there has to be a gap because the thrust measurement itself requires movement of the thruster, but we need to minimize that gap. The waveguide coupling itself becomes a very important calibration point in the whole of the thrust measurement apparatus. And during calibration, we found the loss across this waveguide coupling typically was 0.26 dB, which, if you're on maximum TWTA output power of 619 watts, meant you were actually losing 34 watts out of this this waveguide coupling. And this was clearly a safety issue. The leakage that you get from this is quite significant, and you have to make sure that you keep your test personnel and any observers well clear of the waveguide coupling, and monitor the leakage through a field strength meter. As well as calibrating the power levels through the test system, we must also calibrate the total spurious forces which occur during a test run, which would otherwise lead to a measurement error on the thrust itself. To do this calibration test, what we do is allow the electronic balance itself to carry the full weight of the thruster. Essentially, we just loosen off the suspension adjustment on the top spring until the thruster just sits on the balance pan itself. Now, we carry out the calibration tests with the thruster mounted both upwards and downwards, so we then take obviously the difference between these two configuration test runs. If you look at the plot to the right of the slide, you'll see that we are plotting the detected power in red, the reflected power in blue. Both of these are telemetry values, and the actual force itself in green, the force being measured in grams. And if you look at the the horizontal scale is in seconds. So for the first 20 seconds of the test run, the thruster is stabilizing, and you can see that from the plot of the detected power. It flips up and down before it finally stabilizes at about 20 seconds after switch on. The reflected power peaks during this period and then goes down and settles down to a low value for the constant power condition system for the rest of the run, which lasts about 70 seconds. So the overall test run in this case is the longest of the test runs that we've done, which is the 90-second test run. The power for this particular test run was 300 watts, and we measured a spurious value of force for both configurations of minus 0.102 of a gram. So if you look at the standard deviation over this run. Obviously it varies up and down a bit. You can see the green plot varying up and down around the 0 point. We got a standard deviation of 0.192 of a gram. This was perfectly satisfactory. It's way below the 10 to 1 that is typically used for a maximum error on these sorts of measurements. And in fact, it's fairly close, in fact, almost spot on to the balanced resolution itself of plus or minus 0.1 grams. We've said that for the thrust measurement apparatus, we produced a mathematical model, and the plot to the right of the slide shows you the output from this model over a typical test run. What we're plotting here, first of all, is the temperature rise in degrees C times 10, which is the red line, and three force outputs. One is the force when the thruster is mounted upwards, that's the blue line. The green line is the force when we mount the thruster downwards, and the black line is the reference that we have calculated the force will be as the temperature rises, and you can see that the black line is a constant, as indeed is the temperature rise, the red temperature rise. What we therefore can do is to find the predicted output thrust by basically taking away the reference line from both the up and downward outputs from the model itself, and you simply subtract the reference line to get the predicted output thrusts from the model. Here we show the test data for an actual test run, for a medium power test run where the input power was 324 watts and where the thruster was mounted, if you like, upside down, so that the reaction force is downwards, and therefore what we're measuring on this particular plot here is the reaction force rather than the thrust. If we look first of all at the detected power, which is the red line, you can see, as we've seen before, that there is a stabilization period required before the stored energy reaches a maximum, and the thrust stabilizes at a fairly constant, the power stabilizes at a fairly constant level. The orange line is the interesting one in that it shows the manually applied frequency tracking algorithm. So when we talked about this before, you saw that you needed to first of all put in a frequency offset. You then need to increase that frequency fairly rapidly. You have a period when it's a constant frequency, and then as the cavity itself starts to warm up, the axial length starts to increase and the resonant frequency starts to come down. And you can see the stepped decrease in the frequency from about halfway through the test run. The actual force measurement itself, the reaction force measurement itself, is shown in dark green, and the output from the mathematical model is shown in light green. And the thing to point out which is rather good, is that the mathematical model prediction and the actual measurement peak itself pretty close. We're quite pleased to get this. Why have we got a peak in the reaction force? Well, this is the limitation of the frequency tracking algorithm. Essentially, you have some difficulty in following the actual resonant frequency of the cavity as it heats up, unless you have a closed loop system. and what we've done here is we've shown the effect of the manual frequency tracking algorithm rather than a closed loop frequency tracking system, which would be essential for any flight use of this thruster. You can also see, of course, the very quick drop-off of thrust at 138 seconds when you turn the power off. As a matter of interest, the resolution of this plot isn't that good. Basically, data points are taken every 2 seconds. So you must bear that in mind when you look closely at these test results. Formal tests on the flight thruster were carried out using the rather complicated composite balance that we talked about in the previous slide. But much later on, we carried out a set of measurements, thrust measurements, on what is seen as the classic way of measuring thrust, which is using a beam balance. So essentially you offset most of the weight of the, or virtually all the weight of the thruster by using a counterweight on the other side of a beam balanced on a knife edge. Classic setup. In this case, you can see we also use an oil damper to stabilize the movement of the beam, and we use the waveguide coupling, this time mounted vertically, to allow the thruster to move independently of the fixed microwave source. Now, for this set of tests, which were carried out towards the end of our development phase, we carried them out to investigate the effects of preload on the thrust output from a thruster. We've talked about this before, and what you have to do is to put a load on the thruster so that the increase in kinetic energy due to movement of the cavity itself does not overtake the buildup of the stored energy in the cavity when you first switch it on. So this again is looking at the effect of conservation of energy. We because this set of tests was done much later in the development cycle, in fact 9 years after we did the formal tests of the thrust on the flight thruster, the poor old thruster had been through a number of other research groups who played with it and did all sorts of tests with it to verify that what we'd done was right. And by the time we got it back, the thruster performance was pretty awful. It was typically 27 millinewtons per kilowatt specific thrust, which was way down on what it had been in its best. So, but it didn't matter, because what we were really looking for here was change of thrust with preload, not really looking for absolute maximum thrust. what we were able to do was to enable the beam balance to measure both thrust and reaction force by carefully setting the beam slightly offset from horizontal. And we did this by varying the stop height. And so we could, as I say, measure both thrust and reaction force without actually moving the configuration of the thruster itself. Once again, calibration of the balance was necessary, and this was carried out using standard laboratory weights. Essentially, the objective of the tests on the beam balance were to prove that the preload is necessary if you're actually going to attempt to measure static EmDrive performance. Clearly, if you allow EmDrive to move on an air bearing, you know, the result is pretty obvious. But when you're trying to measure static thrust, if you, for instance, use a pendulum type test rig, you're not going to get very satisfactory results. The essential problem is that any pendulum, whether it's a vertical pendulum or indeed a rotary pendulum, is going to have a zero load at rest. It's, if you like, the experimental demonstration of the early in-orbit anomalies that were found with EmDrive type thrusters. So if we look at the graph on the right, this is showing the variation in thrust. So it's a positive downwards force against the horizontal scale of varying preloads from 0 to, in this case, 1,000 milligrams. So all these measurements are now at very low values of force. We're using a much more sensitive electronic balance to get this data. And the obvious thing you can see from the measurements of thrust against preload is that as you approach each end of the preload range from 0 to 1,000 milligrams, so the thrust, which is around 500 milligrams at its maximum, approaches zero. I mean, this is exactly what you'd expect from the consideration of the theory and consideration of the effect of conservation of energy. We confirmed this by doing a set of reaction force measurements, which is the plot to the left, and you can see there that again, at each end of the load range, in this case a much smaller load range, you see that we go from 0 up to a negative peak and back towards 0 again as the preload is increased. The beauty of this particular set of measurements were that we were actually attempting to get the thruster to lift off the balance, which it did, which we were very pleased to see. You can see that at maximum reaction force, so around about minus 200 milligrams, it actually lifted off the electronic balance pan itself and moved to the fixed stop on the other side of the beam. The dotted line that we show in this particular characteristic is the theoretical liftoff limit, and it shows that we did in fact get liftoff once we'd gone past this theoretical limit. Here we see a drawing of another sort of test rig. This is a vertical test rig where the weight of the thruster itself is counterbalanced on the other side of a fairly large wheel. In fact, what was used was a bicycle wheel for this particular demonstration. But the idea here is we can actually demonstrate liftoff over a small vertical height. Literally, the height is dependent on how long you can make the free waveguide coupling, which again is mounted in a vertical configuration. It provides a good demonstration of how, if you have a high enough Q and high enough power, you will eventually be able to use an EmDrive thruster as a launch vehicle. It does have another very useful aspect, this vertical test rig, and that is when you're working on superconducting thrusters, basically to develop a launch vehicle, you need to verify the effects of Doppler shift under acceleration. So if you make this test rig sufficiently high, you can use it as a drop tower to enable you to measure the Doppler shift under 1g acceleration, if you like, when you cut the string and allow the thruster to drop. It will be very important to understand the Doppler shift effects during this development period of superconducting thrusters.